Hi there, Denny again. I thought I'd try this one a little closer up, see how it feels. Um, this video is going to be an attempt at a brief explanation of quantum uncertainty, the and why it causes problems with our observations. I made a video about relevant inertial frames and how they apply to gravity and our experience of time. At the other end of the scale, size-wise and time-wise, so to speak, we have quantum mechanics. To reiterate the idea of relevant inertial frames, events in space-time are captured in individual inertial frames. Relevance applies when we string them together and have the experience of reality. The relevance is the order in which they appear in our experience. One of the undertakings we have handled recently is observation of the very, very small objects in reality. When we do that, we have to apply large amounts of energy to a very small space. And one of the rules that Schrodinger and all came up with was the idea that quantum uncertainty is the idea that I can look at an event or a particle, say, and with 100% certainty know its position, but not be certain of its momentum. I can also vice versa that. And if I know its momentum with 100% certainty, which I can do, I then no longer am able to know its position accurately. And they work in opposition to one another. So depending on the question that I ask of a relevant inertial frame in an experiment, a particle, say, when I look at it with high enough energy, that energy actually affects the inertial frame itself. Now, as I do the experiment and time passes, because here we are in reality, space-time, the reason that the relevant inertial frames are uncertain in one or other parameter is the fact that I'm using large amounts of energy to observe that inertial frame. When I do that, I project large numbers of electrons at something with a scanning electron microscope, or large amounts of X-rays at something, or use a particle collider to smash two particles into each other. When I do that, what actually happens is I use one inertial frame and slam it into another one so hard that the second frame actually slides back and forth amongst the local relevant inertial frames. So I can know where that thing is now, but looking at it so hard causes it to slide along a vector we call momentum. And that's quantum uncertainty. Also, if I want to know a particle's momentum, I can then do the same thing, but if I ask the question about its momentum, its position will be uncertain because I have to use so much energy to get that information out of the inertial frame. The analogy is staring at a piece of film so hard that actually the other pictures that they took in the roll appear in my vision because I've pushed that particular picture into the other picture. It's a weird idea, but it's not a common idea, and that's why it's hard to think about, because it never actually normally happens. We have to use giant machines to do this. The math came out in the 1900s with Schrodinger and the group that discovered quantum mechanics, and they didn't believe it. Einstein didn't believe it. He didn't like the idea that that sort of thing would happen. So that's what quantum uncertainty is. The idea that when we observe inertial frames very, very closely and with great detail, we actually move them from their position or momentum. Thanks.